Hello, everyone. My name is Rachit Arora. Welcome to this Container Days session on the topic of composition of containers. I really wish I could have done this session in person. I could have got a chance to meet you guys in person and we would have partied together as we used to do a couple of years back. I hope we can meet sometime next year and we'll discuss more on technology, adoption of containers, what can we do more. But let's continue for this session on the topic of composition of containers, design pattern for Kubernetes containers. So a little bit about myself. I'm working as a consulting member of technical staff in Oracle Big Data Service in OCI. I basically come from a team where we provide Hadoop and Spark clusters built on Oracle distribution for Hadoop, our own distribution, offering managed cloud service, which gives you this big data ecosystem as a platform. I'm a very big fan of Kubernetes and containers and have been working with containers and Kubernetes for many, many years. And I call myself as a conference traveler. Like before pandemic, almost twice or thrice in a year, I used to travel, come and give talk to conference, meet many of you in person, and have very detailed and very interesting conversations. I really like to try out food, various cuisines, and I'm a big foodie. Okay, so let's see some of the usage patterns, how many people and companies are adopting containers. They are using them in production, and I have seen people start with adoption of containers, primarily with starting with their build pipelines. And there is also a new trend of adopting Knative based pipelines, which is purely based on Kubernetes. We can install Knative and use this Knative pipelines, which really help you achieve all your CI/CD requirements just using Kubernetes and containers. And many of the pipelines I've seen, like all the test pipelines, almost every pipeline I've seen is based on containers, where you have your test code containerized so that it can run on any environment wherever it can. And the prime use case where almost every control plane in many of the cloud systems is running on containers, purely for their value of very well integrated with service mesh use cases, where I don't have to worry about my blue-green deployment, A/B testing, and I can easily load balance between resources. I can make sure that I get the dedicated resources. So most of the microservice workloads are run on containers and mostly on Kubernetes. And many people use Helm charts along with Docker containers for preparing and sharing the demos, which basically guarantee that if a demo is prepared in my local local machine, it can run on any machine, right? So it's fairly very widely used uses pattern for containers. And many organizations have started adopting to use containers for their analytical workload when it comes to, let's say, running Python notebooks, doing data science operations, even running Spark workloads, which could consume GBs of data. We are running on them on containers. And value we see of using containers is as a cloud provider, to achieve a serverless pattern and giving a serverless experience to our consumers for running these analytical workloads using containers. There are many other use cases where containers have been adopting and the usage has been growing. And And because of this wide range of usages, I see different types of Docker images being developed and being used in production and in their different pipelines. I have seen Docker images can be as small as in few MBs and grow up to GBs and really go more than 20 GB in size. And I've seen them running in production. The build of such Docker images also vary. You may be just doing some hello world or echo statements in your Docker images versus installing conda packages, bringing Python libraries, and the build of that Docker image itself taking many hours to complete. And as the size of the Docker image vary, the time it takes to push to a registry can also vary from few seconds to hours. And same is the case when it comes to creating a container. The time it takes to create a container vary from seconds to even hours in a case that you have purely written a very bad startup script for your containers. With varying size of Docker images, it also brings some challenges when it comes to security scanning. It's a big challenge to scan very large Docker images. Many of the scanning tools are not able to scan these images, and you have to basically divide your image or scan them manually or scan them with alternative ways. And other usage pattern, which many companies who are using containers in production, is they spend a lot of cycles to fix the security vulnerabilities. First, they spend a lot of time on computation resources to scan them. And primarily, the challenge comes when the Docker image is very large. All the effort to get the images scanned and fix the security vulnerabilities can be reduced if we are using small Docker images, so that it can be independently be scanned, fixed, and can be tested and moved to production. So, and this is a cycle which needs to be continued because there are always a new security vulnerabilities which come in production and which needs to be fixed, and this cycle continues. And one more challenge I see many people face with when it comes to usage of large Docker images or more number of Docker images is that most of the time when you run containers, the image for that container will be sitting on your primary OS disk unless you have configured the system to use something like a block. And if you have multiple versions of your offering to be made available, that OS disk kind of get filled. And it can be very helpful if you can break these big Docker images into smaller and have versioning for those smaller images rather than having versioning for your one big Docker image. So as we have seen, the adoption of containers has grown, and in the emerging era of technology, the cloud plays a very crucial role, and the application development become easy with the use of containers. Kubernetes is playing a very vital role in the deployment and scaling of these applications. And as the number of applications which are running on container is growing, we see some best practices which are getting evolved, which are resulting into some of these design patterns which we can reuse and learn from. A few of them are like a single container, which means deploying an application and putting inside a container. It's a simple pattern where the journey of container starts, and in this case, container would contain only one responsibility. and very widely used, and many of you are aware, is a sidecar pattern, which is basically extending the behavior of a container. And in this, container is attached to a parent application container, and sidecar provides supporting features to the main application. One of the very popular pattern I've seen is this ambassador pattern, where the primary goal is to simplify the main container's access to the other services. Like the application container invokes the other container, which acts as a service discovery layer. Adapter pattern is also very widely getting adopted, and it's suitable when we want to keep the communication between the containers very consistent. It generally transforms the primary container's output into the output that fits our application standards. For example, a container can expose our application's monitoring interface, even though it does not implement it in a standard way. A leader and election pattern is to basically replicate the running component so that the load can be shared among the component repeated instances. The distributed systems that have replicated processes contain a common problem of electing a leader, and the application may need to select a leader for replicas running set. Work queue pattern basically focuses on splitting up a big task into smaller tasks and reducing the running time. Init Container is a very well-known practice. I'm sure everybody would have been using it. Like every container includes a configuration concerning to a task, which make it want to do at the time of startup. And basically, if you want to replace some default configuration of an application with the custom application, you can use init containers to do that. That way, I would also like to introduce a new pattern which I have seen evolving, although the composition itself is a standard practice, but adopting within the containers is a new pattern I see growing. And it's primarily helpful when it comes to you have a, let's say, large image problem, and I'll discuss some of the scenarios where this design pattern can be really helpful. But let's first understand the pure definition of the composition itself. It basically means that some different parts come together to form a bigger thing, or form one action together. In the pure tech definition, when a field's type in a class hold a reference of another object, it primarily means we are composing that object in the primary class. Basically, when a class uses another object to provide some all of its functionality. So in the world of containers, we can say that main container uses something from the other container to perform its functions. Now let's discuss a few of the scenarios where we could see a need for such a design pattern like composition. As I discussed earlier, if you deal with Docker images which are very large, for example, a Docker image created for offering Python virtual environment, which could be having a Python runtime along with different libraries, a library coming from different Conda versions, a library coming from different connector versions, a library set coming for offering your application code, and all of them together working in tandem to offer a notebook experience to your data science team. Instead of creating one big container having all these library sets, you can compose them having different versions of individual library sets and offer it as still the same functionality which you could have achieved using one big image. Few more scenarios, like if you have a requirement where you want to mount a running container as a volume to another container. If you want to access the file system of another container from your main container, how can I achieve that? It's been a very big discussion in the community, in the Kubernetes community from the beginning days of Kubernetes. If you're using pure Docker, Docker used to provide this option of using image as a volume, but Kubernetes decided not to give that capability by default. There was some options which I will discuss, like using some of our CSI drivers. We could have achieved that, but it was not there by default. And always the reasoning has been that it can be achieved through different means, using GitHub, of using init containers, and other means. But when it comes to really large size images, those means was not really solving the problem. If you want to basically, if your image build pipeline is running for large to churn out that final big image, instead of building one image, you can parallelly build multiple images, have their own versions, and whenever a fix or a security vulnerability or a version upgrade or library version upgrade is required, you can independently build them and use it in production and ship it that smaller size container to production, rather than building your entire image, running your entire build pipeline to churn out that big container. If you have a use case where you want to offer a container just as a read-only file system and not allow somebody to modify, you can use this design pattern to mount a running container as a read-only file system and use the libraries from that image to your primary image. And again, there are other use cases where you want to do an action on the main container, but you want to control certain binaries and not provide in the main container because your main container is having a user access given, and your main container should only be doing one particular job. But in order to add the capabilities like debugging capabilities for your developer so that they can log into your other container, but still able to access the file system, their process namespace from the main container, you can adopt this pattern of composing different containers to achieve that. So let's now discuss what are the different ways of composition which already exist and some of the new ways I want to share with you. So as I mentioned, this capability of composing has been there for if you're using pure Docker. But when it came to Kubernetes, Kubernetes by default have not provided that capability to mount an image as a volume or to use it as a persistent volume claim. In order to achieve that, you have to either build your own storage driver or use some of the existing CSI drivers, which come other community developers have written. But the problem with those CSI drivers are they are not production ready. You have to take a risk of using them or managing them, right? And one very widely adopted design pattern to solve this similar use case has been Init Container. But key problem with Init Container was it adds to a lot of time to a container startup time. And if that is not a concern, Init Container is a very good option. Other design pattern, as we discussed earlier, was to use Sidecar Container. Like with your primary container, you bring on your Sidecar Container, which can host your libraries. And in order to access that libraries from your main container, it has to be put in a shared persistent file system, which is shared by both the containers. So you're not accessing directly the file system of the main container, but you're doing a copy from your Sidecar container to a shared persistent volume, like a host path or a shared file system, and even using empty dir to push at the time of Init Container from your side container and using that. But all of these options were kind of a workaround to solve the prime problem of composing the containers and with the ability to access the file system of the other container and access the process namespace of the other container. So with Kubernetes version 1.17, a stable feature has been added, which allow this process namespace sharing. We can share the process namespace within two containers, and it's really helpful to solve some of these use cases we discussed, like a log handler in a sidecar container and shell access in a sidecar container to debug problems in the main container. It also provides you the container file system access through /proc/pid. I'll show you one example. You can access the file system of the other container and use the libraries or anything which is there on your other container as if you are accessing from your main container, but still able to compose them, having their own independent images, having their own independent versions of it. So this is an example. For example, I have two containers. Nginx is my prime, and shell access container I am creating, where I've just added a security context and an ability to my shell container and not to my Nginx container. Nginx container is not running with this ability. And when I start this process, it brings up these two containers, and I can log into my shell container. And from my shell container, if I do listing of the processes, I can list the process from my Nginx container and still see in my shell container. So I can do this debugging, and I can access the file system using this /proc/8 and then the file system in that container. So this really opens up various ideas of using this pattern to solve different use cases. So with the adoption of this pattern, I can really break up my big image size into smaller ones, and my image pull time, my container startup time will be really reduced. Instead of pulling one big image all the time, I just need to pull one minor layer or one separate image which is changing. I can patch individual images, and I don't need to be doing one big bang release of one image. I can individually patch them. My build time will be significantly reduced because I'll not be building all the one big image. I'll be building them individually. And more importantly, my Docker files will be manageable. I've seen Docker files growing big in lines, and now I can have very good segregation of my Docker files for each of the different containers. So with the evolving usage of containers, we are seeing some new patterns and designs, patterns coming as guideline principles, which offer some of the best practices which you can use and adopt and learn from them and improve the usage of our containers. So composing of containers is actually in line with a very common programming practices of OOPS, which is actual composition. I hope this session was very helpful. You can reach out to me for further questions, either LinkedIn or to my Gmail. Thank you for your time. You have a good day.
One question that I have, how do you use that kind of composition in production platform?
So I can give you one example where we are in the process of using the composition in purely the example I told you, where we are using Python virtual environments. There different libraries for my Python runtime are coming from, let's say, different conda packages, different connectors. Instead of bundling all of them in single image, we are using this composition where these libraries are coming from different Docker images, and they have their independent lifecycle. And at the runtime, we are composing them. With that, we are able to support multiple versions by composing them at the runtime and not have them bundled in one single image.
Got it, thank you. We have one question that just rose. What is the advantage of your design over layered containers?
So layered containers will still mean your image is still one, right? So it's like you are adding layer by layer by layer. And the problem we are trying to address is when it comes to in production, where we have to independently, let's say, handle security vulnerabilities, which may be coming in one particular Python version. So instead of releasing the entire big image, which has the solution, we will release a very small image where the problem lies, and that will actually fix the production. So we don't have to always keep releasing our one entire big image. We can independently release smaller images and solve, let's say, the vulnerabilities which be coming on a particular section of our image and not the entire image overall.
Nice. Anyone? I have one last question, speaking for myself. What was your biggest challenge when you start working in this composition process?
Actually, we have been looking for a very good solution which could fit all our requirements. Requirements primarily being that the startup time of the container should not be compromised, because we want to offer our customers, let's say, the run times as soon as possible. They don't want to wait for a few minutes. So a solution which could not hamper my startup time of the container, that was the ideal solution. And with this process shared namespace being available, we are able to start composing containers in seconds, right? So all the other options like Init Container or Sidecar, where the copying of the library is involved, it adds to the startup of the container time. So that's what we were trying to avoid.
Awesome. I think we're good for the Q&A. Once again, thank you very much for your talk. It was very interesting. If I can have a big round of applause for our speaker, please.
Thank you.
Cheers.
Thank you. See you guys
Bye-bye.
next year.